Hello everyone, I'm Ju-hyung Oh. I'll present our paper, Post-Guided Enriched Feature Learning for Federated-by-camera Person Re-identification. Federated person re-identification trains local models using only the data collected from each camera. Each client learns each one local model, and only the model weights are transmitted to the server to construct a server model. Using this server model, we extract features from both the query, which is the person we want to find, and the gallery, which contains candidate person. Then, we evaluate performance by sorting gallery images according to their similarity to the query. In the person re-identification, representation capability is important, and thus contrastive learning methods such as triplet loss are commonly used. However, compared to centralized learning, where all camera data are sharing, the effectiveness of triplet loss significantly degrades in federated learning. Triplet loss relies on diverse hard samples. However, in federated learning, each client only has access to data collected from a single camera, which limits pose variation for each identity compared to centralized learning. We visualize the top 5 most similar and top 5 least similar images for a given anchor in both settings. In centralized learning provides hard positive samples with diverse poses. In contrast, federated learning hard positive samples tend to have very similar poses. This observation suggests that sufficient hard samples are essential for triplet loss to be effective in person re-identification. However, such diversity is difficult to obtain in federated settings. To address this issue, we propose post-guided enriched feature learning, which augments diverse poses within each client. Our framework has a local expert model that is trained solely on local data without server communication, and a local global model that is trained on local data and communicated to the server. First, we train the local expert model using standard person re-identification laws. Second, we train a pose extraction module to disentangle pose-relevant feature. Third, using this module, we train the local global model with original features and pose-augmented features. Then we explain the second stage, which is the core of our method. The first component is PKD. In this stage, we separate pose-relevant and pose-irrelevant features from the original feature. To achieve this, we guide the pose-relevant feature to align with features extracted from a pre-trained pose detector. Since their feature spaces are different, we match their relationships instead of feature values. This improves the disentanglement capability of the pose extraction module. The second component is SCM. This step ensures that semantic identity information is preserved in pose-augmented features. The augmentation is performed by combining the pose-irrelevant feature of one sample with the pose-relevant feature of another sample. Then, we reapply the pose extraction module to separate and reconstruct the features. The reconstructed feature should match the original feature. This process enhances the reliability of the pose extraction module. The final component is CR. During the training of the pose extraction module, we use features from both the local expert model and the local global model. This prevents the module from being biased toward either the local or the global feature space. Then we show quantitative performance. We compare our method with feature augmentation methods used in person re-identification, federated learning methods for image classification, and existing federated re-ID approaches. Our method achieves SOTA performance compared to all baselines. In addition, through ablation studies on PKD, SCM, and CR, we observed that applying three components together yields the best performance. We also visualize several experimental research. As shown in the left figure, augmented features are located at the edge of original features clusters. Furthermore, we analyze how often the augmented features are selected as hard samples across training rounds. We observe that augmented features are selected as hard positives and hard negatives at high ratios. These results indicate that our method effectively provides hard samples during training. Finally, we list the top 10 most similar samples for a given query. In the baseline, samples with similar poses are often retrieved even if they belong to different identities. In contrast, our method correctly retrieves samples of the same identity even when they have different poses. This demonstrates that the performance improvement comes from enhanced robustness to pose variation. Thank you for listening.